Hello, today I am going to share with you how to find the equivalent gas flow rate by using a flow transmitter in the field which is designed for or calibrated for different type of gas. What do I mean by this? Maybe let me draw a very simple picture so that you can understand easily. Okay, for example, I have a flow transmitter here. This is a flow transmitter. Okay, installed in the pipeline to measure the gas flow rate. Let's say the gas that flow inside the pipeline is CO2, carbon dioxide. But this flow transmitter is designed for or calibrated for different type of gas. Maybe for example argon, argon. Okay, this one argon. Okay, so as we know, if this flow transmitter is designed for argon or is calibrated for argon gas, so this transmitter can only be used to measure argon gas inside the pipeline, not other different type of gas. Let's say we want to measure other gases flow rate instead of argon gas flow rate. So how do we do that? So we need to know the gas conversion factor so that we can find the equivalent CO2 gas here. CO2 gas flow rate here. Okay, so the gas conversion factor is a GCF, gas conversion factor. You can go to internet and Google gas conversion table or gas correction table. You can find a lot of GCF table there. Okay, this is the example of the table, gas conversion table. So based on this table, I able to find the argon gas conversion factor value as well as the carbon dioxide gas conversion factor value. Okay, so from this table, the gas conversion for CO2 is 0.740, and then the gas conversion factor for argon is this one, 0.998. So the effective gas conversion factor 1 is, okay, in this case, for example, the argon flow transmitter measure the gas inside the piping, okay, and it reads about 120 SLPM flow rate. Standardized liter per minute. This is a unit of flow rate that we use in today's video. Okay, what is the equivalent of CO2, carbon dioxide flow rate? We should take this GCF CO2 value divided by this GCF argon value. Okay, so GCF or gas conversion factor CO2 divided by gas conversion factor argon so that we can find the effective conversion gas conversion factor. So this is 0.740 divided by 0.998. So the value is, let me calculate, 0.7, okay, 0.741. Then for argon flow rate of 120 SLPM, standardized liter per minute, the equivalent carbon dioxide flow rate is 0.741 multiplied by this 120. So you will get 88.97 standardized liter per minute. Alright? Okay, now we move to the more complicated analysis. Let's say I had a fuel flow meter assembled in the line and I want to perform calibration. So what I need to do is I will remove the fuel flow meter or flow transmitter from the pipeline, and then I will connect with our standard master calibrator flow meter side by side, such as shown in this picture. Okay, so this fuel flow meter is connected side by side with our master standard calibrator, which is another flow meter, and then I will connect another pressure regulator here. Then I will introduce a calibration gas through this inlet port, and then this calibration gas will exit from this outlet port. So the gas, you can use any gas. Usually we use a gas that is easily available and is not toxic. In this case, maybe we can use nitrogen N2, or we can use oxygen, or simply air. Okay, usually people will use air because it's cheaper and safer and easily available. Okay, for example, this is our master flow meter. Okay, this is our fuel flow meter. This master flow meter is this one, and this fuel flow meter is this one. Okay, so this is a pressure regulator, which is this one. And now we use the air as our calibration gas medium, and we introduce this air into the hose or tubing or pipeline for calibration purpose. But now the problem is, for example, this master flow meter is calibrated for or designed for this methane gas, and the fuel flow meter is designed for or calibrated for chlorine gas. Meaning this fuel flow meter is only can be used to measure the chlorine gas, and the master flow meter is used to measure the methane gas. So if we use the air as a calibration medium gas for calibration purpose, in today's case, we need to find out the equivalent air flow rate. So how to do so is very simple. We can first find out the GCF or gas conversion factor value for both the chlorine and methane gas, and as well as air. As we know, for air, the gas conversion factor is 0.998. I can show you. Okay, for air, the gas conversion factor values is 0.998. As for methane, the GCF value is 0.763. For methane, this one, 0.763. For chlorine, it is 0.876. So chlorine, this one is 0.876. Okay, so for example, if I introduce, okay, 35 standard liter per minute, this one, 35 standardized liter per minute or SLPM air into the pipeline, the equivalent chlorine gas flow rate that measured by the fuel flow meter will be around 30.721. And this air, which is 35 standardized liter per minute, that flow inside the pipeline will be measured by the master flow meter also. And this master flow meter will reach about 26.759 standardized liter per minute methane equivalent. Okay, so how do we derive all this value is very simple. You just need to use the same method that I shared with you just now. maybe I can share with you here briefly so that you can understand it. Okay, for example, you know, right, the GCF value for chlorine is 0.876, and for the air it is 0.998. If I introduce air into this pipeline, and this air standardized flow rate is maybe for example 35, okay, 35 SLPM means standard liter per minute. So what is the equivalent chlorine flow rate that will be measured by the fuel flow meter? So in order to find the chlorine gas flow rate, we need to know the GFC, or the gas conversion factor. So the effective gas conversion factor 1 is this GCF for chlorine divided by this GCF for air, which is 0.876 divided by 0.998. Then you will get about 0.878. So the equivalent chlorine value in this case will be 0.878 times this one, 35. So you will get about 30.721 standard liter per minute. So you can use the same calculation method to derive the equivalent methane gas flow rate. So that's it. Thank you.